particles, especially tiny ones, have a wave-like property that we can resolve. And we saw that with electrons going through a crystal diffracting. Some particles of the wave hitting at some portions of the screen, some hitting at other portions of the screen, some portions of the screen forbidden to hit. It's if the electrons come through, interfere with each other like waves, and are only allowed to hit certain points on the screen. It actually gets a little spookier than that. If you send the electrons through this experiment, one electron at a time, they still cannot hit certain parts of the screen. I think you can imagine, electrons, a lot of them behaving like waves and interfering with each other. But the electrons behaving like both particle and wave, when they go through that grating, they somehow know not to hit certain parts of the screen. It's a very, very, very spooky property of matter. And from here on in chemistry, we're going to talk about those very spooky quantum properties of matter. Let's start by looking at a classic experiment or a classic calculation, a particle in a box. You can imagine taking a particle that has a wave-like property and trapping it in a small region of space. When you trap it in a small region of space, you get wave-like properties occurring. And those wave-like properties are well defined when you trap the particle. Now, you trap the particle in space. Let's draw a picture of that. A wave-like particle trapped in space, I'll draw like this. I'll say a box of length L, and the particle has to be between here and here. It'll have a wave-like property, so I'll draw a wave-like expression on this box. Now, this wave-like expression I'll call the wave function of that particle. The wave function of that particle will give the designation psi. In this case, psi of x, because this is the x dimension in space. Now, we've already said that the intensity of the wave squared is going to give us an indication of the probability of finding the particle. So the probability, psi squared gives us the probability of finding the particle. Clearly, in this case, the probability of finding the particle right in the middle of the box would be very high if this particle behaves like a wave. Well, how do I come up with these wave functions? Well, I can actually do some mathematics. I can say, write down the physics, the kinetic and the potential energy of the particle, and the boundaries that I'm putting on the particle. And when I do those things, I can solve the differential equation for the particle stuck in this tiny little box. It's behaving like a wave. There are those wave functions psi. These are how the wave functions psi must interact with each other if it's a particle to be stuck in this box. Now, we won't go through all the mathematics, but you can solve this. And when you solve this equation, you get an expression for psi that's not that hard to understand. And it looks like a wave function. There's a sine function, an oscillating sine wave. That you'll recognize from your high school mathematics. Psi of x is sine of x. The length of the box is in there, and another parameter, n, is in there. There's not just one solution to this expression. There's multiple solutions. All the integers n work and give you a solution to this equation. So that means there's not one wave function that works. There's several wave functions that work. You can have a ground state, the smallest value of n, but you can have what we call excited states. Higher values of n also give wave functions, and you can tell what happens. This value n is here in the sine expression. As that integer n gets larger, you'll get more waves appearing in your box. So these functions psi give us the probability when we square them of finding the particle at various locations in the box. We can also say, well, what's the energy of that particle? We can calculate the energy using our expression for the wave function and the probability squared. And we can say, well, I'll rank the energy. These particles increase in energy as n increases. The expression for the energy of the particle in terms of this quantum number, we're going to call it now n, go like the energy of the nth state, n squared, h squared, over 8mL squared. The length of the box, the quantum number, Planck's constant are all in there. So I can then plot out, well, the lowest energy state, n equal 1. We have no n equals 0 state. N equal 1 is where we start our counting. N equal 2, higher energy state. You'll see n goes in as the square. So higher n, higher energy state. N equal 3. We'll also calculate and catalog what we call the nodes, the areas of the box where there's 0 probability of finding the particle. 0 probability are the places where the wave function goes to 0. After you square 0, you still get 0, so the probability of finding the particle at these crossings is 0. And that's a strange characteristic of particles that behave like waves. There's portions of the box where the particle is forbidden to be. So this is interesting. I'll have two nodes, 1, 2, node A, area where the wave function goes to 0 in the high energy state, one node here and 0 nodes here. When the number of nodes increase, the energy state increases. That's a higher energy situation. So here's what I have. I have a wave. I'm bounding it on either side. And like you saw in the demonstration, when you have a wave-like property, you bound it on either side, only certain wavelengths can exist. So half a wavelength, one full wavelength, 1.5 wavelengths. I can't fit 1 1/3 wavelengths in this box, or 1/4 of a wavelength, because the particle has to go to 0 probability at the ends. So if I fix the ends of the box, I put boundaries on a wave, I naturally get what I call quantization. Not every wave can fit in these boxes. Only certain waves can fit in these boxes. And there's a gap. I go from here, n equal 1, all the way up to here, and I skip all those energies in between. I can only have this energy state for the box or this energy state for the box, and no energy states in between. The energy is quantized. And waves naturally do this. It's not unusual to see it. We can demonstrate it with audio waves. Audio, sound, is a wave-like property. And here's a tube of fixed length. So if I want waves to exist on this tube, only certain wavelengths will fit. I'll be able to fit, a full wave on this, a wave on this, a wave and a half on this. So only certain sounds will fit in this tube. That's an interesting characteristic. I can demonstrate a couple of the sounds that fit in this tube. We won't hear when we figure the sounds that fit in this tube, we won't hear continuous sounds. We won't hear boo. Continuous wavelengths. We'll have boo and boo, two individual wavelengths that fit in this box. Let's actually demonstrate that. I'll try to spin this and you guys can listen. There's one wave that fits. There's another wave that fits at higher frequency. Higher frequency, lower wavelength. And there's that low frequency, long wavelength. Two energy levels, and you can see energy. It takes me more energy to get to that high frequency than this low frequency. I wonder if I can get a higher one. I can even get a higher one. That's a beautiful acoustic example of waves and quantization. All you need to get quantization is take a wave and force it to exist in a certain area of space. If you fix the ends of a wave, you get quantization. If you take nothing else home from Chem 1, take home the fact that when you take a wave and you stick boundaries on it, you naturally get quantization, whether it's a matter wave, an electron stuck in a box, or an acoustic wave existing in this little primitive instrument. Matter has wave-like properties, and when waves are bounded, you get quantization. You get a particle in a box.